It's a pleasure to be here today and to be part of this BRE Trust community. So the title of my talk and of my PhD is Capture of Volatile Organic Compounds by Natural Building Materials. I'm supervised by Richard Ball and Martin Ansel from University of Bath and also Andy Dangle from BRE Watford. So I will start with the introduction of my PhD. I will show you the project which I'm involved in and the plan, and then few outcomes that I have so far. So a growing strategy to reduce the energy consumption of buildings requires a combination of increased air tightness and high levels of insulation. A consequence of this is the deterioration of the indoor environmental quality by the accumulation of gas pollutants such as volatile organic compounds, and then the health and well-being of building occupants is compromised. So the indoor air quality relates the air quality to the health and comfort of building occupants. The sources of these gas pollutants are various. So it can be air fresheners, for example, outdoor sources like the combustions from the traffic, industries, furniture, building materials, cleaning products. Well, it's a wide range. So the EcoC, as my colleague explained in this talk this morning, aims to develop new eco-materials and components to create both healthier and more energy-efficient buildings. And this can be achieved through hydrothermal regulation and removal of the air pollutants passively and by photocatalysis. So my PhD is related with the passive capture of VOCs and a bit of catalysis as well, as I will show you later. So this leads us to the objectives of my PhD, which is study the interactions between volatile organic compounds and natural building materials, and the outcomes are to understand how materials behave when they are exposed with these gas pollutants and to contribute to the development of new materials for passive control of indoor air quality. The plan to achieve this is to study the interactions between VOCs and building materials. So basically we place our materials inside of environmental chambers. And first we study the emissions from the materials themselves, so we know what is coming from the materials. And then we challenge these materials with VOCs. So we dope the chamber with the polluted air, and then we see how much these materials are adsorbing and desorbing. And then I've made chemical and physical characterization of these materials so I can correlate their behavior with their properties. So the materials that I studied, it's a wide range. So I studied insulation materials, inorganic coatings like lime mortars and clay plasters, and also wood panels. So these are the traditional materials already commercially available. And then some new materials were developed by me and by some colleagues from the project. So, for example, we combined lime mortar with TiO2, like my colleague did, lime mortar with Nisocell, new clay plasters, combined also lime mortar with sheep's wool, and MDF panels with walnut shell. So this is the rig that I used to do these desorption sources experiments. Basically, it's composed by three main things, which is the clean air generator and the humidification system. And then we have the VOCs and formaldehyde sources, where we can dope the air. And then the chamber. So this lab-scale chambers has 2 liters of nominal volume. And we control the humidity and temperature through the whole experiment. So the rig has two lines going from the air generator to the chambers. One line is the clean air. So with this one, we study just the emissions from the materials themselves. And the other one is the dopant air, where we can study the adsorption, desorption experiments. So the VOC chosen for this study was toluene, limonene, and dodecane, and also formaldehyde. Formaldehyde is a very volatile organic compound. We choose these ones because they are different in terms of chemical conformation, polarity, molar mass, and boiling point. So then we can see the effect of these properties on the adsorption, desorption. So how does this work? So we have inlet air with some amount of VOCs, and then the material inside of the chamber will absorb some of these organic compounds, and then we have the exhaust where we do the sampling of the air. Materials are enclosed in aluminum tape, so only the surface is exposed to the air, as we have in the real world. Then I've tested in a room-sized chamber built at BRE. This chamber has ventilation temperature and relative humidity controlled. It has also LED lights, so we can do photocatalysis in there. And 3 sampling locations, so I can see the concentrations of VOCs inlet, center, and outlet of the chamber. For the analysis of VOCs and formaldehyde, for the VOCs I sampled in a 10x tube, which is composed by high adsorbent polymer, and then analyzed by gas chromatography and mass spectrometry. And the formaldehyde is sampled in the NPH cartridge and then analyzed by high-performance liquid chromatography. For the material characterization, I studied the physical and chemical properties, and I used scanning electron microscopy, MIP, BET for surface area, and then several techniques to assess the chemical composition of the materials. So I spent part of my PhD at BRE facilities in Watford, especially for the AAQ assessment, and then the materials characterization is mainly based in university. So in these graphs, you can see the emissions from the materials themselves, so where I have the only pure air going into the chambers. And in terms of formaldehyde emissions, materials that emitted more were obviously the wood panels, because the resins used to bind the wood fibers are based in urea formaldehyde resin. So it's from where the formaldehyde is coming. For VOCs, almost all materials emit very low quantities of VOCs, apart from the wood fiber, which emitted furfural. This is related with the degradation of the hemicellulose. For the adsorption desorption experiment, so our rig has 6 chambers, so we can test 5 materials at the same time and having 1 empty chamber. So in this empty chamber, we know the maximum concentration that we are doping the materials. And then by comparing the concentrations in the empty chamber and in the chamber with materials, we know how much the materials are adsorbing or desorbing. This is the kind of curves that we got from that. So going for the materials curves, toluene was the least adsorbed VOC, and for dodecane was the most adsorbed. This is related with the conformation of the molecule of this compound. So dodecane is a straight chain. It goes very easily to the material pores, while toluene is not going that easily. So this graph shows a bit better how these four materials were performing in the adsorption-desorption experiments. So we can see the lime plaster was the material that adsorbed more all four VOCs, and natural wool performed good with the formaldehyde. This is because the proteins that is in the composition of natural wool, and they react with this VOC formaldehyde by chemisorption. So yes, we know that lime plaster is performing in a better way than the other materials, but why this is happening? So I studied their microstructure to see the pore size of these materials, how is the surface. And what we can see is the laminated MDF, which didn't absorb almost anything, as you can see here. And this is because the surface of it is very flat, so there is no pores. The surface area is very small compared with the other materials. And the lime plaster has very small pores, high surface area, and thus the adsorption is very good on this material. I assessed also the chemical composition of these materials. So we know that the radicals from the cellulose, like the OH, is reacting with these VOCs, and also ionic radicals in the materials like the calcium from the calcite as well. So not only the microstructure is playing a role in this adsorption-desorption experiment, but also the chemical composition of the materials. So going for the Walnut Mdf, why we use walnut? Well, in iron, millions of tons of walnut shell and almond shell goes to the landfill. So it's a big problem for them. So people start thinking in using these materials in building construction. So they added this walnut shell into the MDF resins, and then they studied the formaldehyde emissions from these materials, and they observed that by increasing the walnut shell, the formaldehyde emission decreased. So then we also followed that study, and we added walnut to the resin prepared for these MDF panels. These materials were prepared by Bangor University, one partner of our project. So we confirmed that by increasing the content of walnut shell, the emissions of formaldehyde decreased, and also we did the adsorption-desorption of these materials of formaldehyde, and we observed that materials with higher amount of walnut adsorb more formaldehyde and desorb less. So with this material, we can improve the indoor air quality. Trying to explain why this happens, well, by increasing the amount of walnut, we are changing the microstructure of the material. So we are increasing the surface area. And also, I went a bit further, and the walnut shell surface is very porous. So that's why these materials are absorbing formaldehyde and VOCs. This is a study that I did with the materials prepared by my colleague Andrea Gianpiccolo. So this is a lime mortar prepared with the titanium dioxide. And I observed that by increasing the content of titanium dioxide, the uptake of VOCs was increased as well. So then I studied the surface area by BET, and it's proved that higher surface area, higher the amount of VOCs absorbed. Okay. This is a comparison between lime mortar and clay plasters, and we observed that the clay plasters absorb more VOCs than the lime mortars, and this is because the clay plasters has these irregular shaped particles from the clay, and thus the surface area is higher. This is one of my last experiments that I did with lime mortar with wool. The idea with this is to improve even more the adsorption of VOCs by the lime mortars. So we know that the natural wool has good ability to adsorb formaldehyde. So why not to combine the lime mortar and wool to improve the adsorption of formaldehyde? And we observed that, for example, if we have a polluted room with 300 ppm and we apply this material, the concentration will be decreased by 93%. So that's good. Then we did some tests in the big chamber with we covered one wall with MDF, and we observed the reduction of limonene and dodecane. The same for lime and clay plasters, which improved indoor air quality inside of the chamber. And then the last experiment is a combination between adsorption in dark and photocatalysis. So what I did, I turned off the lights inside of the chamber and covered the windows, so I make sure that the inside of the chamber is in complete dark conditions. And then I run the test for 1 week, and then I turn on the light to start the photocatalysis, and then observe the uptake of VOCs in both phases. So from this graph, you can't say if there was photocatalysis or not. So what I did, I measured the difference between the inlet concentration and the concentration in the center of the chamber during the absorption phase, so dark phase, and then in the photocatalysis. What we observed was that the uptake during the adsorption and was less than during the photocatalysis. So this means that we had photocatalysis. So to summarize, can we improve indoor air quality through building materials? Yes, indeed. We can by choosing emission-free materials as a start, and by using materials with good sink effect, such as lime mortars and clay plasters. We know that different VOCs will have different interactions depending on the chemical composition of the materials, and the physical characteristics and the chemical composition of building materials have a really important effect on the adsorption, desorption of VOCs and formaldehyde. And to finish, this is my dissemination. I have some published papers in a conference and journals and more to come up. And that's it.
Excellent, thank you.